Let's take a look at the ground fault circuits and some fusing considerations. I'm going to go ahead and start by looking at the fusing. I'll start with this circuit here. I've got a bigger version of that right here that we can look at. Now, on this circuit, you'll notice that there's a lot of fuses. We have fuses up here on L1, L2, L3, which is our power circuit. And then we have fuses that are going to our transformer. So let's first of all take a look at these. If for some reason this fuse blew, and this fuse could blow for a number of reasons. Most likely it would be that somewhere over here the load had an ampacity issue and it would blow that fuse. Well, if this fuse blows, well then the line to the transformer is going to go down, which means that this whole circuit down here is going to go down. So blowing L1 or L3 here is going to bring not only your load down, likely, you make it into a single phasing situation, but it's going to take the transformer down, which is going to take the control circuit down, and because this would have main contacts in here somewhere, it's probably going to bring this down, okay? Now, there's the next fuses here. Let's say these are good. These are fused in the transformer. So some reason this side of the transformer shorts, or we're drawing too much voltage, or shoots too much current in one of these pops, well then it's going to bring down the transformer. It's going to leave the power circuit intact, but that means that if the transformer goes down, then everything that here is going to die because the secondary is going to come down. So that's a second level of fusing. Well, these fuses are probably, let's say these are not going to blow because of operation that's occurring here in the control circuit. In the control circuit, fuses are going to blow because you've got a short here. So notice we've got other fuses going on here. So the way that these fuses work are we've broken out individual rungs with their own fuses. We've got different rails that have their own fuses. And then we've got, I guess our main master control relay rail with its own fuses. So let's just start to look at this master control relay. So this master control relay is on a fuse, and it's a selector switch here. So when the MCR goes on, what that does is that closes these contacts here, and now this part of my control circuit is going to be working. So now I've got my logic here for my switches and my holdings and starts and reverses and everything, but this won't work unless I turn on the master control relay. A lot of times the master control relay is on memory as well in case there's a dropout. But if for some reason one of these fuses blew, well then the master control relay is going to go down, which means that this is going to open up, and not only would I not get any voltage on these rails here, but because this opens, it's like a double kill. This whole control will go down, okay? What these fuses are doing out here, and what this fuse is doing out here, these are isolating different processes or different items. For example, let's say we had all my fuses here are good, everything's good, I've got the control relay on, I've got my logic going, the circuit's working, and what happens if for some reason this solenoid sticks and it gets caught into an inrush situation, and that's when the current ramps way up. Instead of coming down to steady state, it just keeps going, and it blows this fuse right there. Well, what's going to happen is everything else is still going to work here, okay? The only issue is that solenoid A is not going to work. So we'll be able to figure out pretty quickly that everything is working here. We can put our multimeters on and fluke and find out where voltage is. Like I said, we would start, first of all, by checking on each side of the load. So if you start going here, this is good load, good, 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 oh, bad, then you can move right to this fuse right here, and you would find that it's shot, but the entire process kept running. So that's why these fuses are here, just to isolate individual components. These fuses here, for some reason, something went bad in this part of the process here, and let's say this fuse popped. Well, that's the same thing, that the main control here is still working, so that because these control relays here control whether these rungs are true or not, we can still bring these rungs in. We can still turn on 3CR, which would still close this and still close this, and then we could take a look at this rung and try to figure out what is going on, and we could work our way back up to here and find out that this fuse blew and it dropped down, and it dropped, even though these rungs are on, it dropped out multiple rungs down here. So what this fuse does, it drops out this process, but it keeps the control on here, so that maybe gives us some different troubleshooting, or it could keep other processes running. Maybe just this entire process here is what goes down. Okay, if that makes sense. So we have these fuses here that are going to bring down the complete control. These fuses here that are going to bring down a portion of the process. And then the third level is the individual fuse on the device that would just bring that device on and allow quite a bit of stuff to run. So this is the highest level fuse that's going to bring everything down. And that's the lowest level fuse. It's just going to bring down the device. Okay. Now when we go and we take a look at the ground detect circuit, that's what you're going to be analyzing right here. Okay. So what this is this has an ungrounded secondary. So a grounded secondary would have a ground right here, okay? And then we wouldn't need this fuse, but ours is not grounded. So what does that mean? Well, if this had a ground to it, okay, then if there was any kind of a short or a fault on here, each side of the load is run directly to earth, okay? Which means that if you had a short circuit on any one of these things, this fuse is going to blow because there's going to be current flow to earth, okay? But we don't have that, so we have an ungrounded secondary, so we need two fuses, and we need a way to monitor if there is a ground fault, okay? Because this system right here is not being brought down to the earth in the same way if it would be grounded here on the secondary, okay? So we would have a ground point here. This point here would be connected to our system or our panel, and it's going to have a load on either side. So if we get any kind of a short or a ground or a ground fault, it is going to be affected by this point. And so I guess a similar item, if you're familiar with cars, is that the entire car, the frame, everything is part of the electrical system. So you can bring your current into one side of your device, and then the other side is just the entire system or the entire car, okay? So what this does is, let's say we had a fault here, and this is what you're going to do. If you had a fault here from, let's say, B, a ground fault, and it was actually touching, it'd be the same as a wire that was brought to this ground, because this represents our system here, okay? If you had something short to the frame, it would be to here, okay? Or A or whatever. But let's say we had a short here to E. So what is the flow of electricity? Well, we have a couple of flows of electricity. and what we're analyzing is the flow through here. So if I look at this run, because this is closed, it's going to be true through there, okay? Assuming I haven't pushed the start button, then that control relay is not on. The electricity is going to take the path of least resistance, okay? So it is going to come to here, or it's going to come up that ground. And then at this point, it's going to then try to get to the neutral side here. And what we have here in the way is a light, okay? So if we have a short here to E from this point, this light's going to come on. Before, if we didn't have this short, both of these lights would be on dim because the flow of electricity would be automatically through here regardless. And so this would get 60 volts, and this would get 60 volts, and they'd be dim. But once we got a short here, the electricity no longer wants to come down here and go through this first light. It wants to take the path of least resistance and just go right into the second light. So at that point, this isn't going to get any voltage, and this is going to get 120 volts. And it's going to come on bright. So when that comes on bright, you know that you've got a ground fault on this side over here of the circuit, okay? Now, as you start working your way through here, you'll see that sometimes we'll create the ground fault from C or from A, and the electricity will pass different ways. As you draw it with the marker here, you want to follow it and create the path of the least resistance for this flow, and it'll say, you know, whether you push the stop button or start button or whether the relay's on or everything like that. So that's a brief description of the lab, and you're going to use a highlighter to indicate how this is going, okay? We're going to take a look at a grounded versus non-grounded. So here, I'm going to my next item, and what we have here is a grounded secondary. So you'll see on the grounded secondary, there's only one fuse. The ungrounded, there was two. And this is an earth. So each side of these loads has a hard contact to earth. So if there's any short in here, this is going to go straight to earth. You're going to get a massive amp draw, and this is going to blow this fuse right here, okay? So a couple of things are grounded circuit requires only one fuse, okay? And so when you got a problem in here, blows the fuse, this system is down. You have to find the problem. You have to fix the problem, and you have to get your multimeter out and fix it, or else every time you put the fuse in here, it's just automatically going to blow, okay? And that's pretty safe though, because any ground, any electricity that's extra, it's going to ground to earth, and the operator is safe, can't be electrocuted. It's safe, but the drawback is your system is down. You have to find where the ground fault is, or you're going to keep blowing fuses. So grounding forces reference to earth to one conductor of the system allows for one contact to complete the shock circuit. So we get the one contact, it's grounded to earth, and we have the shock circuit, and the shock circuit is going to bring that down. Ungrounded systems allow the system to float, and it requires two contacts to complete the short circuit. So now we just don't need one short right here to ground that's going to blow the fuse. When we do the two, what we have is we kind of have a floating system. And so in the most ideal way, I guess you could think of it this way. Let's see if I can have that double up again. There it is. So here's my ground detectors. So in an ideal situation, let's say this whole control panel right here was isolated. It was not part of the electrical system at all. It's not grounded to it. Let's say it was mounted on rubber, so that this was its own standalone item, and that we were grounded here to the panel itself. So if we were to get a ground fault, or something touched metal and it touched the entire control panel here, where, well, there's no earth, it's just this panel is looking just at itself, and therefore you're not going to blow a fuse, because you need, instead of just having, one shock circuit that would blow this, you would need two. You'd have to get to either side of this transformer, if that makes sense. And so what happens is this panel can have a fault, like we just showed here. For some reason, I had a fault up to here. Okay. Well, assuming this is on, assuming that was on, I'm going to have flow of electricity to that light. And so instead of these being on just dimly, this light is going to go on. And then I can tell, you know, based on my troubleshooting, this can help me troubleshoot kind of where this circuit is. Now I can come in here and I can switch things off and on and start seeing if this light returns to, you know, normal, where it's half lit, or if I start pushing things, what's causing this light to come on bright. And because I can go through and try all the circuit like that, then when I finally get to the rung that causes this to come on bright, well, then I know that that's starting to put me in an area where my fault is. Okay. So that's kind of the quick premise on the ground fault. And there's a difference between, you know, grounding and bonding and talking about earth and everything like that you'll get into in some later classes. But what you're going to do is you're going to try and look at the logic and see how this goes. So a couple other things real quick. To take advantage of the benefits of an ungrounded circuit, a ground detect circuit is needed. And that's, once again, where you can leave the circuit energized and troubleshoot it a little bit. You got to be careful, though. You don't want to electrocute yourself. You must provide notification of the ground fault. So that's why we have the ground fault light. It allows tracing the fault before the system is shut down by the second fault. And so that's where you could just kind of go through each of the operation of each rung and find out which rung is causing the light status to indicate where it's at. It provides some troubleshooting assistance depending on the fault's location, and it uses those two push-to-test lamps in series. Okay, so that is a quick summary of how that ground fault circuit is going to work here. Okay, there's a couple of other advantages of the ungrounded system. It is going to reduce the downtime because of that, and it allows for maintenance personnel to kind of schedule maintenance, because you can leave it up as you kind of work your way through some stuff. And remember, if you have an ungrounded system with a temporary ground, it's just like a grounded system. That's the best case where there's no real hazard to the operator when you have the grounded system, because any faults are going to be taken away by the ground. So whether it's a temporary ground or normal ground, but you're gonna blow a fuse if you have a problem. You're not going to be able to troubleshoot this kind of on the fly. Maintenance personnel need to be aware of the hazards of all systems that have become grounded as far as the potential for shock is concerned. Okay, so there you go, and good luck with the lab.